Hello. In today's video, we're going to go over CFM demand. Wait a minute, we did that. CFM demand part 2. So in one of my groups, somebody was telling me that I was using it incorrectly, and they were asking why my constant was different than the one they had. And they posted a paper of where that constant came from, which I hadn't seen before. It was a great help to me. And I should have probably questioned it years ago. The constant I was using came from Stan West, who was a math guy 25 years ago. And I never really questioned it. For the most part, it did what it needed to do, and I didn't worry too much about it. But with this paper, I got to see the actual formula and the guy talking about how he came to that. And now I am questioning what it's doing. In this formula, what he had was a conversion supposedly to get you to 28 inches like on the flow bench, airspeed, which of course you need, that's the main component of what we're working on, divided by 2, which is actually just a holdover from this, because you need like half of the RPM, but he was trying to make a single constant, so I moved it over here. And then volumetric efficiency. And from that, he figured out a constant, which would then give you the CFM. Now, in looking at this formula, my first expression, or my first experience was, it has no business having volumetric efficiency. And we can talk more about volumetric efficiency, but what really controls volumetric efficiency is the camshaft and the closing point of the camshaft. And I've done videos on inertia ramp, and the Z of the cam that I talk about in inertia ramp basically runs hand in hand with the volumetric efficiency. The reason you don't want this in this particular formula is if you increase airflow in a cylinder head, you essentially increase the cross section. Even if you've just ported it in order to make it better, you've increased the effective cross-sectional area. This affects airspeed. Airspeed drops, and then you need RPM to get it back. So volumetric efficiency has no business in this particular formula. And what I posted on the group is you need to really just leave that out and redo the formula without volumetric efficiency and put that new constant in the formula. And that will work. I ran a motor real quick here, and it came out to like 274 CFM at 6,500. So if you want to do that and just leave volumetric efficiency, that's fine. That's the most glaring error in this particular constant. Now, I kept looking at this formula over the last week, and I really don't like it. I don't like any of this. This conversion to go to 28 inches from essentially what, because we're kind of doing like mechanical flow. This is the X amount of volume we have, so that's the flow. That's considered mechanical. And to get you to 28 inches, like you see on the bench, all this really is 1.055% change. That's nothing. Your airspeed could be slightly different. This part of it is meaningless. And like I said, the 2 belongs really over in this formula, and the volumetric efficiency shouldn't be there. So that leaves us with airspeed going into 1. Well, when you divide something into 1, you're really just doing the reciprocal, and that's so you can multiply as opposed to divide. So even doing that is somewhat meaningless. So that means we can pretty well get rid of all that. Get rid of that whole thing. It doesn't matter. And so I rewrote the formula without that and without going to a constant. Now, this is CID and RPM, just like air. Feet per second, that's your airspeed. Number of cylinders, and the tube that we stole from the other formula to divide your RPM in half. And that'll give you CFM. Now, running the same motor, I got 282. You're saying, well, that's different. Well, it's different because I changed the airflow. I changed the feet per second. What he used over here is 0.57 Mach. And remember, the limit we have on airspeed and the reason engines peak is really because of the speed of sound. That is the controlling factor. Now, when you have a port, the valve opens up, the speed of the port starts picking up, you reach maximum speed, the valve's going shut, that kind of starts closing the airflow down, the airspeed in the runner drops, so you have a curve. And so you're not really at the speed of sound all the time. So you have an average. Now in normal values, we tend to use 0.55 Mach as considered the more acceptable number. He used 0.57. I've seen guys use 0.6 Mach, which you can certainly do. Now remember, the speed of sound is going to vary some depending on the pressure in your intake, vacuum, and what temperature the air is. That's also going to affect it. So we're going to have some variation anyway. But in general, I prefer to use Mach 0.55. And so that comes out to 214 feet per second. And you're welcome to plug in on this formula any number that you seem appropriate. And we will talk a little bit more about that in the future. Now, that gave me a slightly different number than that. Technically, both are usable. Now, remember, I was also told I was using it wrong. This formula was designed in order to give you minimum cross-sectional area. That was its purpose in life. And the way I was showing to use it was talking about where the motor's going to peak. Now, it is how it's going to work, but let's talk about what it was meant for. Now, in the same paper, he gave 147 CFM per square inch as to what you can expect to get. Now, that number has been kicking around for years. I have never liked it. I have never found it to be accurate. That is not a good number. Now I know why. The reason is he added in volumetric efficiency, which shouldn't be there. And I'm guessing he worked backwards from a known value on cross-sectional area, because this is 20% high and this is 20% high. And so it gets you to the right cross-sectional area if that's all you're using it for, but then it doesn't make sense for the way I'm using it. And that's why I always kind of took the number with a bit of grain of salt, is that, yeah, this is the ballpark of where I'm going to be, because it never got right on the money. And now I know why. And so I should have researched this a long time ago, but let's kind of walk through how I use it. Like I said, I do not like this number. If you take volumetric efficiency out, do not use 147. You need to reduce that by 20% or 24%, because I think that was the number he was using in the paper. Now, I have taken an actual engine because I want to show you what I was actually trying to show in the previous video with CFM demand. The engine has a limit. Your limit is airspeed. This formula is designed to show what kind of flow you can get in a given engine and what RPM that's going to peak at, because they all peak at Mach 1, or basically Mach 1. You know, it might be 0.98, 0.99, I don't really know. But it's basically at that number. And so that's what this formula is about. It's about how much air you're going to move at your peak air speed. And so I have taken a motor. Now, I have a tendency in these videos to use other people's data. I do that for a reason. A, you can go verify it, and B, you don't think I've manipulated the data to get the outcome I wanted. I just go get the data and run it through and show that it works. So this is an Eric Weingartner motor. And I'm not picking on Eric. I like Eric a lot. He gives me the data that I need to actually crunch numbers. And so in this particular motor, which was recently run, it's a 427, 10.3 to 1 compression, 2.5 minimal cross-sectional area, 248 cam on 109 plus 3, 640 lift, so it's kind of aggressive. The head flow was 325 at 700 and 319 at 600. Remember, we're kind of halfway in between that. So we could call it 322 or something. It don't need a precise number. We're not really using that. So this motor made 625 horsepower at 6,500 RPM. So that's why I used 6,500 over here. That was its peak RPM. 427, 6,500 RPM, that's what I put in the formula. If you want to use the regular formula, that came out to 274 CFM. And if you want to use my new formula at a different airspeed, that came out to 282 CFM. Remember, this is just Mach 0.55, which is considered the normal number you should be using. So I didn't manipulate this. So anyway, if you look at the motor, the question is, how much air did we actually use in the engine? And I hope some of you guys are looking back at what the motor produces and trying to see what your port work brought to the table. It's always good to know where your horsepower is coming from. Now, I've plotted out this cam using inertial ram, and it's basically a Z of 1. That means its engine is basically 100% volumetric efficiency, or right there. They go hand in hand. They are not perfectly on top of each other. There are some other variations in what happens. But they get close enough that that's what we can use. So with a Z of 1, 100% volumetric efficiency, I need to decide what else is bringing power to the table. And one of the things, which I talked about in the previous video, was compression. This is 10.3 to 1 compression. Each point of compression is going to give you about 3%. 2 points of compression, going from 8 to 10, is about 6%. We're a little past that, so it's 6.9%. And that's how much we are gaining from compression. So if we divide that into the 625 and figure out how much of that horsepower is not from compression, what we wind up with is 584 horsepower. Now, remember, fuel will also affect what it is. If you're running methanol, which could be 18-20% gain, if you're running mostly ethanol, 85-90% ethanol, that's like a 7% gain. If you're running a oxygenated fuel, that could easily be 3 or 4% gain. If you're doing anything in the way of boost or whatnot, of course you have a gain from that. All that needs to come out of it in order to figure out what you're doing. This is a regular gasoline motor. In fact, they were touting how they were using just regular pump gas. So I don't have to worry about taking those other power adders out of what's going on. And this number is important, especially if you port heads. You want to know what your port work is bringing to the table so you can either do a better job later on, or you can maybe improve on what's going on here because you see where the power is coming from. Now, with 584 horsepower, that's 73 horsepower per cylinder. Now remember, when we look at a port on a flow bench, we're looking at an individual cylinder. So to get that to CFM, Superflow, for their flow bench, came up with a number years ago that's held really true. They did a lot of testing and they showed that 0.26 horsepower per CFM. what they were trying to show is what you see on the bench will equate to real horsepower in the motor. And if we use that number, what we come out with is 281 CFM that we used to generate the power this motor made. Now, if you look over here, my number is 282. That's pretty close to 281. So that shows you part of the reason this motor is peaking is because of airspeed. You basically used the airspeed because you peaked at the correct RPM. Now, it could also show you you are way off. There's something wrong. And you'll have to figure out what's wrong with the motor in order to get it to peak where it really should be peaking at. So, in this case, one of the things that I look at is that minimal cross-sectional area. Now remember, this was 2.5 minimal cross-sectional area, 2.5 square inches. So if we take that 281 CFM that was from airflow, because we don't want compression in it, we just want the airflow, and we divide that by 2.5, that comes out to 112.4 CFM per square inch. Now, if you look over here, my number is 108 to 120, not this 147. This is much more realistic. This works in the real world. The reason that I have a variation here is it depends on what kind of motor you're working on. Now, remember, those bends and whatnot in an engine are going to affect how well you utilize that minimal cross-sectional area. Now, if you have a race motor, a tunnel ramp, a straight runner, a raised port, a good shot at the back of the valve, you've basically straightened out the assembly as best you can. Well, you're going to get better effective use of the cross-sectional area, and that might be more like 120 CFM. Now, if we're talking an OE motor, dual plane intake, you're coming down, you're making a sharp 90, you're having to wrap around, you're coming in a big curved runner, you might have a port mismatch, you've got a tall short side, you've got all these bends, you know, the pushrod wall is in the way, all this stuff is in the way. Well, that's going to affect how well you actually do at the cross-sectional area. And so in that case, I use like 108, 110 for a regular motor. And that gets me much more in the realistic view. That also shows up here. Like I said, this is 112. He did some work to the intake. It's a little better head. He had ported the head. It was a better design. And so he gained a little bit past that normal 110, but still basically limited by cross-sectional area. He did not get to the 322 CFM that the port flows. And so technically that says that the flow bench is lying to you. You cannot make that power if you can't get it through a cross-sectional area. And that is part of why we do this nerdy math exercise, is to see where we're standing. You can say, okay, well that port did great. I should have made, way more power. I should have been up at, 680, 700 or something. It's not going to get there. It's using what it can. It's almost at 300. Now, the problem is, as most of you know with porting, is your minimal cross-sectional area is usually your biggest problem. It's mostly, if it's a standard V8, it's at the pushrod. And you can use offset rockers, weld up the port, sleeve the pushrod hole, try and push the wall back, raise the runner a little taller. You can do a few things, but you are not going to massively impact your cross-sectional area. You might get this up to 2.6, 2.7. If you really work hard, maybe 2.8. But technically, you almost need 3 square inches to make really good use of that 325 CFM. And you're just not going to get there. And that is part of the reason you do this exercise. You now know where to look. It's not in how the port is shaped. It is flowing better. It is using the entire cross-sectional area. You're at a good number. You are actually got a nice port. It's just you are stuck with a little low cross-sectional area because there's just no material left to take out to make that any bigger. And so you know that's what it's going to do. If you're not going to live up to the RPM you want to do, say this needs to be a 7,000 RPM motor, well then you know that what you have to do is increase the volumetric efficiency at that peak RPM. And the way you're going to do that is by moving this closing point. You're going to go to a bigger camshaft and you're going to nudge that up, and then you're going to make better use of that, and then you'll be at like 109% volumetric efficiency, something like that, in order to get you up to that 7,000 RPM where you want to be. And that kind of explains why an engine makes what it does and why I look at CFM demand. There are limits, just like I said in the previous video, for what the cubic inch size and the RPM can flow. If I was to figure this at 5,000 RPM, I would be a way lower number with either one. And you would see that technically my cross-section area is too big at that point. I'm able to move way more CFM than what RPM I'm trying to target. And that's not right either. And that's why we do all this nerdy math in order to figure out where we're sitting and know how the engine's going to behave. Once you have an idea on a motor that you haven't even run yet, you can see, okay, I have this kind of flow, I have this kind of RPM, I need this kind of intake, I need this size of carburetor, I need to be going to, I'm not going to make that 7,000, so let's gear the car for 65. I think it'll be good at 65. We have enough cubic inch to meet the horsepower we want to make. I have enough flow to meet what I'm going to make. I have enough cross-section. You know, if I can deal with fuel, hey, let's pump a little more compression in, get a little more power. You can quickly design a motor to do what you want it to do. Whether it's going in an RV or a truck and it's all about low amp power, or if you're working on a race motor and you want to turn 8,000 RPM and just haul ass, well, you can plan it. And that's what all this is about, and that's how I use it. And I'm not sure this guy really had a good handle. So use a little logic and maybe go with a better formula. And if you want, you can figure feet per second. You can swap in the formula the airspeed for the flow. You can put flow down here. So it's CID times RPM and flow times 8 times 2 and divide that into the previous number, and that'll give you feet per second. So if you have enough data, most of us do not, you could figure out a different number to use for your feet per second that you think is more consistent with the type of engine you're dealing with. And that would then improve what you're coming up with when you're planning the next motor. And so that's how it all goes. And if we need to, post something in the comments if I didn't cover it well or doesn't make sense. We might have to have a discussion about Mach and what number we should be using for airspeed. But that's another video. So I wish you well in your projects. I hope this helps you out. And my lights just went out.